Since 2014, he is a director of Laboratoire de Mécanique Modélisation Précise Propre and professor at Aix-Marseille University. His main research topics are computational fluid dynamics, aerodynamics, aeroacoustics, uncertainty quantification, aerospace engineering, urban physics, turbulence dynamics and modeling, and numerical methods. He is a well-known specialist in aeroacoustics and Lattice-Boltzmann modeling. In 2010, Professor Sagaut obtained Grand Prix de l'Académie des Sciences in the field of science and engineering, and it should be noted that each year the Academy of Sciences nominate only 3 scientists from the world for such prize. Professor Sagaut is the editor-in-chief of the Journal Computers and Fluids. He is the author of more than 500 publications, and his main famous textbook is Large Eddy Simulation for Incompressible Flows, an introduction. It has been cited more than 4,700 times. He supervised 68 PhD students and 15 postdoc fellows. All of them are enjoying successful careers in academy or industry. So Professor Sagaut, I give you the floor to start your talk.
Thank you very much for this very nice introduction. I will now share my screen. Okay, do you see my screen?
Yes.
So thank you very much also for this very nice and very kind invitation. I feel very honored to speak today. And I hope, of course, that the next time I will enjoy meeting you in person in Russia. But okay, we all know that. Okay, so my talk today will deal with the recent works in my research team, and I have to acknowledge the great job of all young people working with me. You can see a few names here, but as you mentioned, more than that were working on Lattice-Boltzmann method in Marseille. And my point today will be to give you some flavor of what we have been doing using Lattice-Boltzmann method for the simulation of complex turbulent flows. I am not, of course, going to give a lecture about basics or fundamentals of Boltzmann methods. Just to remind you that instead of looking at fluid dynamics, solving continuum mechanics equations, like the Navier-Stokes equations that are based on macroscopic quantities such as temperature, pressure, density, viscosity, and fluid velocity, we are now working with the Boltzmann equation, which are based on a statistical description of the fluid dynamics at, let's say, an upper level, which is the particle level. And for each particle, of course, we can define a kinetic energy, momentum, collision process between particles. And of course, after that, we all know that there are some statistical quantities associated to such a fluid, like for example, the mean free path of small molecules. Okay. And the Lattice-Boltzmann method can be seen as a very specific discretization of the Boltzmann equation, because looking at the Boltzmann equation, we can see that we have a 7-dimensional problem. We have 3 dimensions for space, 1 for time, and 3 dimensions for for the velocity of the particles. And of course, defining a computational grid in 7 dimensions would be by far too expensive. It can be done in some cases, but for most existing engineering application, first, it will be by far too expensive in terms of CPU time, also for memory requests, and sometimes it's not necessary, meaning that we can find more simple models that will give us reliable data for engineering applications. And the Lattice-Boltzmann approach is such a method because we are decreasing the dimensionality of the problem by defining a given finite number of discrete velocities, meaning that we are not using a grid in the velocity space, but we define some not fully arbitrary. Of course, it has to be done in a smart way to get an efficient method. But we define a discrete set of discrete velocity. And of course, after that, we have the same problem as for the Navier-Stokes equation, meaning that we have to define a grid in space and, of course, to run a time-dependent simulation to capture a steady effect. But the dimension of the problem will be the same as for the Navier-Stokes equation. Okay, just having a few words about the equations themselves. What I've put on the top in the yellow part is the original Boltzmann equation. This is a continuous Boltzmann equation. We can see that we have a linear advection term on the left-hand side because C is a particle velocity. It's not the fluid velocity. And on the right-hand side, you have the collision term. So the term that is used to model the fact that particles can interact. And of course, this collision term, there is a formal expression given in the 19th century, but it is too complex and too expensive to be used for practical simulation for engineering problems. And you have to find models for that. And a well-known model, this is a BGK model, which is here on the bottom equation, where the collision process is modeled as a relaxation process toward an equilibrium state, which is denoted F0. Okay, and this is a simple linear relaxation with a relaxation time tau. And there is a well-known analytical expression for this equilibrium function. This is a Maxwell-Boltzmann distribution. And I just remind you the formula here. And it cannot be used like that for simulation in LBM for many reasons. The first one is that it is expensive. And the second one is that it is genuinely non-linear terms. And to get an exact, to compute an exact integral or moment of this term, will be very difficult. So it has to be simplified. It has to be further simplified in order to get efficient numerical approximations. Once you have computed your distribution function f, solving the previous equation, of course, you can reconstruct your macroscopic quantity for engineering. This is density is defined as a zeroth order moment of f. Momentum is the first order moment, and the energy is associated to second order moments of f. And of course, there are some conservative properties that have to be fulfilled in order to recover the correct macroscopic Navier-Stokes equation, or something which is equivalent to that. And to do that, your collision model has to preserve some collision invariance. And it means that if you look at the equation, that the integral over the different velocity of your collision term has to be 0. For momentum conservation, the first order moment has to be 0. And for total energy conservation, the second order moment has to be 0. And I have to say that there is a famous Russian school of people who have worked on discretization of Boltzmann equation, on this kind of equation, and that we are still using these famous old works from the 70s and the 80s and the 90s to develop our models. Just to have a general look at what is referred to as Lattice-Boltzmann method, the general picture is the following one. You will find a growing literature about so-called LBM methods, and you will find that there are many, many different things that are described as Lattice-Boltzmann method. So just to give you not my definition, but the kind of method I am using, okay? First, of course, starting from the top to the bottom, you have to define a physical collision model. For example, you have to model the kind of interaction between the particles. What I'm going to use is something without any, for example, electric field or magnetic field. So collision will correspond to shocks between particles. From that, of course, you can close your Boltzmann equation in a theoretical and continuous way. And after that, of course, you have to work to derive an efficient computational model. And you have two things to do. First, as I told you, you have to reduce the dimension of the problem by defining a set of discrete velocities instead of discretizing the full velocity space. And at the same time, you have to work on the definition of a collision model that will be physical in the sense that results will correspond to fluid dynamics, but it has to be computationally efficient, meaning that it has to be robust, accurate, and that the CPU time associated to this collision model has to be, let's say, affordable. Once you have done that, you are still dealing with a continuous equation. And of course, you have to handle spatial discretization and time integration. And if you look at the existing literature, you will see people using either structured, unstructured, or meshless approaches. And in the present case, we are using in my team structured grid, Cartesian grid, to be more precise. And once you have defined all these things, to solve your equation, you can use either finite difference, finite volume, finite element, discontinuous Galerkin, spectral Galerkin. All these things have been published for the Lattice-Boltzmann methods. What we are using in my team is a mix of finite differences and finite volume methods. And last point is that Lattice-Boltzmann method is nothing but fundamental equation for fluid dynamics. But of course, you have to supplement it and to close it for some additional physics. For example, for phase change, for combustion, for turbulence modeling, you have to add some new sum models to close the equation and account for new physical mechanisms. And once you have done all these things, you get your LBM method. Just to show you that if you change only one pieces in the puzzle, for example, switching from finite difference to finite element, of course, you will get another method with some possibly very different features in terms of stability and accuracy. So what I'm going to present today is based on our in-house model for the collision term, which is referred to as hybrid recursive regularized. Hybrid because this is a mix of classical Lattice-Boltzmann and finite difference for the computation of stresses that appears in the collision term. It is regularized in a recursive way in order to improve stability and to filter out some spurious numerical modes that may be present in LBM. On rho, because looking at the zeroth order moment of our distribution function, we recover density. It's also possible to define other methods in which, for example, in place of density, you can recompute directly pressure. And of course, the next moment corresponds to momentum. This is pretty classical. The time integration is based on this is classical on a strong like splitting. We first compute the collision step. This is what you can see here, defining a F star, which is an auxiliary solution corresponding to a relaxation toward equilibrium. And after that, we have the streaming or advection step. And using a smart change of variable, it's possible to compute that in a very efficient way in terms of CPU by just doing some kind of shift in the computer memory, and that corresponds to a second order accurate discretization of the advection step using a kind of Lagrangian method and to recover the second order accuracy without using an implicit method, so it's fully explicit. We have to use a change on variables. Okay, but these are details. I'm not going to discuss all these things. So at the very end, we have a fully explicit method that is pretty local because we only need the first neighboring cells to compute the new solution at a given cell. And we have something that is stable. The main feature is fully explicit. It's compact. It's well suited for a uniform grid. And of course, sometimes we need to refine the grid locally to handle complex geometries. And this is done using a local grid refinement with some octree implementation. And of course, for engineering applications, we need to be able to describe complex geometries. And this is done in practice using a kind of high-merge boundary models. And this is, of course, the only way you have to describe arbitrary geometries in a Cartesian grid. Another advantage is that it also enables some very efficient automatic mesh generation. So a few words about turbulence modeling that I'm going to present today. Remember that Lattice-Boltzmann method is at the same level of description as the Navier-Stokes equation, meaning that this is a continuous equation, or this is a basic equation for fluid dynamics. And after that, for example, if your grid is too coarse to capture all scales of a turbulent flow, you need to add a turbulence model. And of course, here there is no black magic, meaning that solving Lattice-Boltzmann equation, the turbulent closure problem is the same as for Navier-Stokes equation. And this is why you use almost the same turbulence model as for the Navier-Stokes equations. And you can also have the same hierarchy of discretization of turbulent flows. What I'm going to show you today are results coming from large-GD simulation. Large-GD simulation is an unsteady three-dimensional approach in which you assume that most of the turbulent dynamics is captured on your grid. So the grid is assumed to be fine enough to capture, let's say, 90% of the kinetic energy of the flow. Now, if you coarsen the grid, then there are some so-called hybrid Ranz-LES method in which the turbulence model is more complex, including most of the time some additional auxiliary equations. On using a more complex model, we assume that we can handle coarser grid because the turbulence model will be able to capture more physics than simple models that are used for large-GD simulation. And of course, you can also ask for Navier-Stokes equation. You can run some steady simulation with Ranz, in which all the turbulent dynamics will be buried by the Ranz model. So now I'm going to illustrate some recent applications. The first one, this is just a kind of demonstration. This is a turbulent flow at Reynolds number about 1.8 millions in the subsonic regime. This is a Ranz simulation with a wall model. Wall model because we are using a Cartesian grid approach, we cannot refine the grid in order to have the famous y plus equal to 1 constraint fulfilled, meaning that we cannot use a classical turbulence model like that. We have to do something on the first cell. And the things we do is to include a wall model, and we are defined a power law wall model.
Входящим потоком, синий нисходящим. Мы видим, что вытянулись волны.
Excuse me. Do you hear me?
Yes, we hear you.
Because there was someone.
Yes. I don't know what it was. But...
Okay. Sorry. And so this is typically the grid you can see. And you can see that, okay, we have refined the grid with embedded grid near the solid surface. And now what you see, this is done with the Spalart-Almaraz model. So you can see on the top left the mean velocity. And here this is something which is almost equivalent to the turbulent viscosity. And after that, of course, you can recompute some polar plots. For example, on the top here, you have the lift on the drag coefficient of the NACA wing versus the angle of attack. And we have two grids, grid A and grid A0, corresponding to a medium and a coarse grid. And we have experimental data associated to the crosses and a solution obtained by the X-Flow solver from NASA as a red symbol. You can see that for the lift, it's pretty accurate. And for the drag, we have two different solutions because, of course, drag of such a clean wing is very small, so computational errors are visible, but we are close enough to experimental data to use such a data. And on the bottom part, you have the distribution of pressure coefficient for two different angles of attacks. And you can see that here we are close to experimental data. You can also use that, and this was one of the main interests of Lattice-Boltzmann method for massively separated flows. Because here the details of the boundary layer physics are not so important. Most of the physics is somewhere in the separated flows. On here, the use of Cartesian grid is not a problem. And of course, this is, you can see this is a landing gear, a simplified landing gear. It corresponds to an experiment carried out in Germany at DLR in collaboration with ONERA in France. So this is a reference test case for used by Airbus now to calibrate models for this kind of simulation. So the number is about 1.6 million. This is still subsonic. And this is a typical bluff body with massive separation. On here, of course, because the difficult point is to capture the correct separation point along the landing gear on both the main gear and also the wheel. And here we had to improve the whole models in order to account for favorable pressure gradient and adverse pressure gradient effect on the physics of the turbulent boundary layer. It was published recently. And you can see that, okay, we have some nice three-dimensional and steady simulation. And here you can see that we have three regimes corresponding to gamma equal to 1, 2, 3. So gamma equal to 1, the black thing corresponds to a favorable pressure gradient region, while the green region, for example, corresponds to an adverse pressure gradient in which the no-slip boundary condition has to be used because the boundary layer is not developed enough to use low glow or something like that. Okay, now if you look at the results, this is the mean velocity in the wake of the landing gear, and this corresponds to another slice downstream in the wake. And you can see that we are close to experimental data that correspond to the symbols. Now, if you look at the pressure coefficient on the wheel, okay, you can see that we have probes here. So on the left wheel, there is a full distribution of pressure coefficient. And you can see that symbols, meaning experimental data, are very close to our simulated data. And this is mostly done at Airbus, for example, for acoustics. So the problem being the noise generated by landing gears near the airports and near urban areas during the landing phase. And in order to compute the noise, what is looked at is the pressure spectrum at the wall, meaning at the solid surfaces of the landing gear. And here, experimental data correspond to the black solid line. You can see that there are some peaks corresponding to characteristic frequencies, and they are well captured by the numerical simulations. Something more complex in terms of geometries. Okay, this is basically a clean 2D wing, but with icing. Okay, and what you can see here, this is a photo of icing measured in a wind tunnel, and after that, from that, there is a scan, and the people have derived a kind of three-dimensional printing of the same shape, and it is now put on a wing model. And after that, you can do some measurements in wind tunnels. Okay, this was done in Germany a few years ago, and we have some measurement with a resonance number equal to 1.8 million. It's still in subsonic case. And of course, you can see here that the geometry of the ice part is very, very complex. And to do that, only immersed boundary condition can be used because the geometry is so complex that defining a structured grid able to capture all details would be a nightmare. It's not impossible. It would be very, very complex. And on that, we run an hybrid Rancellius simulation based on the DS by Spalar and his Russian colleagues. Strelets and colleagues. And here you can see typically the flow for different variants of the turbulence model, but typically the wake topology is the same. You can see that we have, of course, separation here near the leading edge because of the ice part. It's fully three-dimensional for sure, because the ice part is also fully three-dimensional. And here the color corresponds to the intensity of the eddy viscosity. You can see that the main difference between the model is not the topology of the flow, in the value of the eddy viscosity, because the important part for the flow is the boundary layer dynamics. After that, in the wakes, it's less sensitive to the details of the turbulence modeling. And of course, after that, you can do some comparison, experimental data. So at a given location on the wind tunnel model, there were some pressure probes. And you can also, this correspond to the crosses here, the dark crosses that correspond to the experimental data. And with the three variants of the detached simulation approach, we got results that are pretty close. Okay, here we have some problems if you look at the pressure side. It comes from the fact that it's good here, it's not good here, because there is a recirculation bubble here, which is fully three-dimensional. And in experimental data, they didn't average over the span-wise direction. So this is a single location data, while in our case, we can run things like that, meaning averages. And if you look at the polar plots, you can see that the grid B corresponding to the fine grid simulation are very close to experimental data if you look at the lift versus the angle of attack. And for the drag, which is more sensitive, at low angle of attack, we're very close to experimental data. And what is missing in the experimental data, this is the corrected data. Because you can see that here, for example, on the lift, you have two set of experimental data. This is the same experiment, but there is a correction law applied to data to account for some, let's say, specific feature of the wind tunnel. It has been done for the lift. It has not been done for the drag at all for angle of attack. So we don't know what is the exact value we should recover here. And of course, after that, you can go to more and more complex things. Here, this is on the top, this is another trap-wing model, which is not a toy test case, but this is a three-dimensional wing with small aspect ratio. So this is easier to compute because you don't need to have this long wing to discretize. All the physics is there because you have the slats, you have all the details of the eye lift, and you can see that here experimental data correspond to pressure on the model at some locations. And that both on the fine and the coarse grid, we are pretty close to the experimental data on all parts of the eye lift system. And after that, of course, you can go to even more complex things, such as, for example, the DLR F6 model. This is a transonic case. And here you can see that the picture, this is from the top and from the bottom. There are two parts. On the top, this is what you can get using the SU2 unsaturated finite volume grid solver developed at Stanford University. So based on Navier-Stokes. On the bottom part correspond to what we got using our Lattice-Boltzmann approach. And you can see that flow topology is very well recovered using Boltzmann in that case. Okay, and after that, this is the courtesy of Airbus. This is the kind of simulation that they are doing using Lattice-Boltzmann. So they are addressing real engineering problem, meaning full-scale aircraft, with details down to a few millimeters of the full aircraft configuration, with grids with up to several billions of cells for engineering applications. Okay, I see that my time is over. Thank you very much, and I will enjoy answering your questions.
Okay, thank you very much for your very interesting presentations. The questions, please. You could ask in Russian or in English.
Okay, may I ask a question?
Please, okay.
Thank you for interesting talk. You know, it's very tempting to use Lattice-Boltzmann approach, but it's still, there is no clear understanding how we jump from discrete particle motions to continuous media. Can you explain more, maybe in some simple way, How you do it?
Meaning that how to switch from the Lattice-Boltzmann to macroscopic Navier-Stokes equation?
Yes. How you do it? Yes, you use Lattice-Boltzmann approach to study continuous flows. Yes, continuous media.
That's it.
How you do it? It's a main, main reason for cautious attitude to Lattice-Boltzmann approach.
The switch is there, but here this is a continuous equation. The real Boltzmann equation is a continuous equation for a distribution function. Okay. What we do is that we discretize the distribution function space, so the velocity space, in order to minimize the complexity of the problem. And after that, the point is that what we should enforce is that density will be recovered as a zero Fodor moment, momentum, and so on. Okay. So the trick is that when you discretize your velocity space, that correspond to quadrature points in the velocity space for these integrals. Okay. And after that, this is a choice because you can show that you can recover the same value by just integrating not f, but only the equilibrium part of f. And here, the game is that you should design your set of distribution function on your approximated equilibrium function. So not this one, because with this one, you cannot compute the thing I'm talking about exactly. So you are going to define some typically polynomial approximation such that these integrals will be exact.
Okay.
And while still enforcing conservation. But it's not trivial, meaning that after that, of course, we are dealing with numerical methods, so there are some discretization errors. And in Boltzmann, in LBM, the kind of discretization error you have to deal with come from these things, okay? Because if your set of distribution function is not chosen in a good way, you are not going to compute, for example, all this integral exactly. And then you have to deal with errors.
And how you verify your choice? You compare with experiments on numerical simulations?
Yes.
And what are the
there
limits?
Also some analytical developments, okay?
The limits of Lattice-Boltzmann approach, can you describe?
Yes.
Or it can be used for
I
everything.
have the same question. What are limitations?
What are limitations? If you look at the
for
Boltzmann
application
equation,
of Lattice-Boltzmann to fluids.
I think that the main limitation is that to be very efficient, you have to use uniform grades. Okay, so when you have massively separated flows over bluff bodies like a landing gear, they're very efficient. But if you would like to compute with that attached flow at high Reynolds number over flat plates, for example, you can do that, but it will be much more expensive than Navier-Stokes equations.
Okay.
After that, we know now how to handle compressible flow with shocks, also combustion. The problem will not be, is that possible? Because it is possible, because at the very end you recover some macroscopic equations. But this is a problem, is efficiency compared to Navier-Stokes equation. And in some cases, you have better to use Navier-Stokes equation for sure.
Okay.
And what about boundary layers? So it's not good when there is pronounced boundary layers, yes?
Yes, this is what I was talking about during my talk, is that you can compute it, but the grid will be so fine with LBM that it will be much more expensive than Navier-Stokes for attached boundary layer.
Okay, these are in some sense disadvantages. And what is the advantages in comparison with Navier-Stokes?
This is a CPU time unit for the same results. What is measured by Airbus and Safran in France is that they divided the cost of simulation by a factor 10 to 20 compared to their best Navier-Stokes solver. And also the time they need to define a grid. For example, something like that. Once you have once you have imported some definition of the solid surface, you need less than 2 hours to define the three-dimensional grid and to run the simulation. While you need several weeks for an engineer to design a classical structured grid with multi-domain approach on such a configuration. Okay. So here they are saving money by saving engineering time.
Okay. We do not have more time, but maybe one short questions. Do you have some questions? I see the comment. Thank you for your interesting lecture. Is the Lattice-Boltzmann simulation applied to river hydraulics, in particular to simulate dynamics of large rivers? It's a question.
I don't know. Sorry.
Yes, I also don't know. Okay.
I don't know, sorry.
Because there are also turbulent flows and eddy generations. So
yes, I think of course you can run hydraulics. We do that for nuclear engineering. Liquid flows in tubes and complex things, but for rivers, I don't know because it's not a field of application. But if you send me an email, I can try to answer you. I can spend
okay, because it's a question actually from my team.
Okay.
Okay.
So send me the email because otherwise I may maybe just forget to answer, and I will do my best to find you something on that.
Okay. Okay. So we need actually to start the second lecture. So thank you very much again, Professor Sagaut, for this very interesting, comprehensive talk about this lattice